Dear friends, I am Professor D.G. Trivedi going to take your second practical. Opamp as an inverting amplifier. Opamp can be utilized as an inverting amplifier also. It can be utilized as a non-inverting amplifier also. If the input is given at the inverting terminals, then the output is 180 degree out of phase. That means output will be RF upon R1 minus side will be there. That means if the input signal is going to be the positive going signal, the output is going to be negative going signal. Normally, the amplifier is having infinite gains. So you can see that in this synopsis, the ideal characteristic of the op-amp is given: infinite voltage gain, infinite input resistance, zero output resistance, zero offset voltage, bandwidth is going to be infinite, CMRR is going to be infinite, and slew rate is supposed to be infinite. This synopsis also I am going to give you as a PDF file. So don't worry about these things. This is also I am going to upload it. So it is having a two inputs. You know that Opamp 741. It is utilizing the split power supply plus 12 volt minus 12 volt. So here you can see that in a board. This is the board for Opamp as a inverting amplifier. This is written here, Opamp as an inverting amplifier. This is the power supply, plus 12, minus 12. Positive terminal of this one, that is a plus 12. I am connecting to the 7 number terminal of the Opamp, and minus 12, that is going to be connected to the 4 number terminal of this Opamp. So this is the way it is connected, and the common terminal is connected to the common reference point. So this way the power supply is connected. Now this is between pin number 1 and pin number 5, there is a potentiometer is there. So the end points of the potentiometer is connected, and from the 4th number terminal minus 12 volt is connected to the potentiometer variable terminal. The output of this one is initially connected with the DC voltmeter, just like previous practical. Now we have seen in a study of Opamp that input offset voltage is generated. That means V1 minus V2, the difference of the input voltage has to be 0. But instead of 0, there is some voltage is going to be generated. And that voltage has to be nullified by giving some feedback voltage between pin number 1 and 5. We can give through the minus 12 volt through the potentiometer, and will make the output voltage 0, which is right now not 0, it is 7 millivolt or something. You can see that, and that's why I have connected the pin number 2 to the through the 1 kilo resistance to the ground, and pin number 3 is directly connected to the grounds. You can see that this terminal is directly connected to the grounds. Pin number 2 is directly connected to the grounds. I have not given any inputs. Both are connected to the grounds. Still, there is a some output voltage is visualized here. Plus 87 millivolt or something is going to be visualized. You can change this potentiometer here right now. I can vary this potentiometer. And if I will make it another way around, this potentiometer, this voltage is going to be minus 116 millivolt or something. So using this potentiometer, I can vary the output voltage from minus 116 millivolt to plus, this is decreasing, and this is going to be plus 88 millivolt or something. So I have to adjust this potentiometer such a way that the output voltage will show 0 millivolt. That means whatever error is there, that error I am going to nullify here using this potentiometer. You can see that it is reducing. Because it is a plus and minus voltage, it can reduce this one. So this is a minimized, make it minimize this one. So you can see that. This is minus 0.3 millivolt, approximately 0. So this is called offset null conditions. We are offsetting the input voltage. which is because of the circuit impedance, whatever the input offset voltage is going to be present in the op-amp, that we are removing or we are nullifying by giving external feedback voltage. And this output voltage in the meter, you can see that it is exactly 0, because using this potentiometer you can make it to positive or negative, but you can make it 0 also, and that way the error becomes 0. So this is the first part for either utilizing op-amp as an amplifier, as a inverting amplifier or non-inverting amplifier. This error has to be made 0, and that condition is known as a offset conditions. And for that, this is the circuitry. You can see that this is in the synopsis. This circuitry, can you see the circuitry figure 2? Circuit for offset null. Feedback resistance of 10 kilo ohms is utilized. Then pin number 2 minus sign, that is through 1K it is grounded. Pin number 3 is also grounded, so V1 minus V2 is 0. And pin number 1 and 5, between that there is a potentiometer is connected, and variable terminal is connected to minus 12 volt. Pin number 4 is connected to minus 12, and pin number 7 is connected to the plus 12, and the common reference voltage is going to be there. Output is connected to the DC multimeter, where we have measured that output voltage is going to be 0. So this way we have made the offset null. By making this offset null, now we can utilize this op-amp in this condition without disturbing this potentiometer. We can utilize as an amplifier. This condition has to be done in both the cases, either it is inverting amplifier or non-inverting amplifier. So now I am interested to utilize as a inverting amplifier. That means input from the signal generator, I have to give it to the inverting terminal of the op-amp, that is pin number 2. So pin number 2, from the signal generator I am giving the live terminal to the pin number 2, and the ground I am going to connect to the common terminal. That way the input AC voltage I have given now from the signal generator, and I can vary the input frequency with the input voltage of 0.1 volt or 100 millivolt. I will adjust, and I will adjust this 100 millivolt and will be measured in AC millivolt signal. This is your AC millivolt. So previously we were measuring the DC voltage, and that's why we have utilized the multimeter. Multimeter is having a limit that for higher frequency this multimeter will not work properly. So we are utilizing this accurate meter for that of Opamp, that is nothing but AC millivolt meter we are going to utilize here, and we'll give the input signal is going to be 100 millivolt. So this AC millivolt meter I am utilizing first to the input side of this one, and I'll adjust first of all 1 kilohertz frequency. You know that when we are utilizing as an amplifier is nothing but converting DC energy from this power supply it is taking and converting into AC energy, right, according to the AC input signal. We are utilizing the standard frequency initially to adjust all these things. That is going to be 1 kilohertz frequency is going to be the standard frequency. You can see that 1.08 or something. So this is going to be 1080 hertz frequency I have adjusted, 1.08 kilohertz. That is the input signal I have adjusted. Now what is the output that input voltage amplitude is there? that I will be measuring here. The input is very, very high. I want to adjust in 100 millivolt. So the input can be adjusted through the level amplifier, level of this one. This can be adjusted here, and I will be watching here on this meter. I am giving the sine wave signal. Instead of square wave, what is the input I have to give? Which kind of frequency I have to give? The input is supposed to be sine wave. So from this function generator, the first button, this is the function, different functions. It can give the sine wave, it can give the square wave, it can give the triangular wave, etc. So I am utilizing this sine wave here. And this is the level knob. This level knob with the attenuation is there. So if the higher input voltage is there, that can be attenuated using this one, 20 dB and 40 dB, total 60 dB input can be attenuated. Input voltage is not changing here. I have to verify here whether this is working or not properly. Yes, this meter is working properly. So something is wrong with this. First I will be measuring the input voltage. Now I am taking the output not from the TTL, but it's normal output across the 600 ohms or something. Then it will change. So you can see that this is the knob I am wearing. This is in a 1 volt range. So I want to make it 100 millivolt, or I'll put it in 300 millivolt range, and I'll adjust this one a 100 millivolt. So 1, 2 and 3. This 3 multiplied by, so it is in a 300 millivolt range. So 1 indicates it is going to be 100 millivolt. So input's frequency is going to be 1 kilohertz and its amplitude is going to be 100 millivolt, which I have adjusted now. Now what I will do, I will vary the input frequency and measure the output voltage for different frequency, keeping input voltage 100 millivolt only. And I will be testing this as an amplifier. You have studied the RC couple amplifier, you have studied a different type of amplifier in a previous semester. This is using the Opamp as an amplifier. Things is going to be the same. Output voltage upon input voltage is nothing but your voltage gain. And that means I am changing the frequency and measuring the output voltage. Now you can see that this is going to be 1 kilohertz frequency. I am starting from 100 hertz frequency. This is approximately 104 hertz frequency is there. The output voltage is still 100 millivolt. You can see that it is in the 1 only, and the range is going to be 300 millivolt. That means it is going to be 100 millivolt only. So the input voltage 100 millivolt I have adjusted. Now I am connecting this meter, AC millivolt meter, to the output, and you can see that it is amplified version is there. This is in a 3 volt knob or 1 volt knob. That means output is going to be approximately 1 volt. You can see that I am keeping in the 3 volt range. So this is going to be 1, 2 and 3 volt. So output voltage is going to be 1 volt is there. Input voltage was 100 millivolt. That means 0.1 volt, output voltage is going to be 1 volt. The gain of the amplifier is 1 divided by 0.1, that is approximately 10 volt is 10 is supposed to be the gain. And theoretically the feedback resistance is going to be 10k and input resistance is going to be 1k. The ratio of this one, RF upon R1, that is going to be 10k upon 1k, that is also going to be 10. So whatever we are getting theoretically, the same gain we are going to obtain here experimentally. And you can see that the input signal is going to be positive going here. The output signal is going to be negative going, sine wave. And that's why it is called inverting amplifier. If it is non-inverting amplifier, input will be given to the non-inverting terminal and the input and output signal will be in the phase. This way we have to change the input frequency. This is going to be 100 Hertz and it is 100 millivolt and output is going to be 1 volt, so the gain is going to be 10. Now I am changing this frequency from 20 Hertz to 30 Hertz, 40 Hertz up to 100 Hertz. Then after 200 Hertz, 300 Hertz up to 1k, then 2k, 3k up to 10k, then 20k, 30k up to 100k, then 200k, 300k up to 1000k, that is going to be 1 megahertz. This way I am changing this frequency and finding out what is the output voltage is going to be there. You can see that this is a 1k frequency. The input is 1k frequency. Still output is going to be approximately 1 volt, no change. That means the gain is still to be 10 only. Now I am taking only the major steps. Now the input frequency is kept 12k. The output voltage is still to be 1 volt. That means gain still remains to be 10 only. So mid frequency gain is almost constant. Now if I am changing this input frequency, you can see that up to 100 kilohertz, this is going to be the input frequency is going to be 100 kilohertz. Output voltage has decreased. From 1 it has decreased to 0.6 or something. That means 0.6 volt. That means gain has reduced from 10 to 6. You can see that at 100 kilohertz the gain has reduced from 10 to 6. Still I am increasing this frequency 200k or something. The gain is still decreased approximately 350 millivolt or something. That means 3.5 gain will be there. So at higher frequency gain is decreases. Now what you have to do? You have to draw the graph. That is the graph of frequency response. This will be your table. Observation table is like this. Application of input frequency is going to be from 20 Hertz to 20 kilohertz. So the first column is observation number, second column is the frequency which is varying logarithmic scale, because you are going to draw the graph on logarithmic scale. 20 Hertz, 30 Hertz, 50 Hertz, 100 Hertz, 200, 300, 500, 1k, 2k, like this way, 3k, 5k, 10k, 20k, 30, 50, 100k, 200, 300, 500 and 1000k, like this way. For that you have to measure the output voltage. The third column is the output voltage, and the voltage gain is nothing but 20 log V0 upon Vi. V0, whatever we have taken, for a lower frequency it was 1 volt and input voltage was 0.1 volt, so the gain was 10, and you have to take the 20 log of the gain of 10, etc. That way you have to find out the gain in logarithmic scale. Now you have to plot this graph. You can see that this graph, on x-axis the frequency will be there and this frequency will be in the logarithmic scale. That's why it is called semi-log graph paper. Voltage from 0, 5, 10, 15, 20, 25, etc. That means this is, you have already taken log, so this is the normal range, 5, 10, 20, 15. So this graph is known as a semi-log graph paper is here. You can see that from the lower frequency up to this frequency, gain remains almost constant. that is approximately 10, and then after it is reducing slightly, and then at a higher frequency the gain is decreases. So whatever the maximum gain is there at 1 kilohertz, lower to that minus 3 dB if you are taking, you will get corresponding to that somewhere here the points will be there, and that points, if it cuts to the frequency, that frequency is your F2, and here F1 is going to be 0, because this op-amp is utilized as a DC amplifier. Starting from 0 hertz the gain will be maximum, that is going to be mid frequency range, and F2 is your bandwidth. F2 minus F1 is normally your bandwidth, but F1 is going to be 0 hertz, so F2 will be the bandwidth of this amplifier, and that bandwidth of the amplifier you have to find out from here. It will come approximately 80 to 90 kilohertz. So this is your second practical. Op-amp as inverting amplifier is completed. You can see that circuitry of the op-amp as amplifier. The first circuitry for the offset null will be there. Both the inputs are grounded. Second circuitry, the input is removed from here, but input is connected to the AFO, and input is measured priorly, and it is adjusted 100 millivolt. So this is your function generator or audio frequency oscillator you can connect here, and that should frequency vary from 20 hertz to 1000 kilohertz. Pin number 3 is grounded. This is your RF amplifier, which is going to be 10 kilo ohms, and R1 is going to be 1 kilo ohms. So this ratio RF upon R1 is going to be 10. So gain of the amplifier theoretically is going to be 10. Between these two, we are not disturbing the potentiometer because we have already adjusted for 0 error. That's why this will not be disturbed. That's why we are doing the offset null. And here at the output we are connecting AC millivoltmeter instead of DC volt or multimeter, and that way we are finding out the frequency response of inverting amplifier. The same thing can be done for the non-inverting amplifier. Thank you very much, friends.